Today, students, we are going to start in our iBook notes on page 11. See, I've written that at the bottom. And we will be studying today 1-2, understanding rational numbers, and moving on to understanding adding rational numbers today, which is section 1-5. Following our iBook notes, you'll need to have your workbook out and we'll work on the examples together. So at the top here, 1-2, understand rational numbers. We'll start with some little details which include the first section called terminating decimals. So terminating decimals is exactly what it means, that the decimal has an end. And some examples of that would include 0.85, and it actually converts to 85 over 100 because the place value of the 5, the last digit, is in the hundredths place. Make sure I say that right. This simplifies to 17 over 20. Another example would be negative 0.5. Now it has a negative symbol and it's a negative number, but it is not an integer. If you recall when we discussed integers before, they were whole numbers, 0, and their opposites. So they cannot be decimals and they cannot be fractions. So this can also be written as negative 5/10, because the 5 is in the 10th place, which simplifies to negative 1/2. Okay? So terminating decimals can be written as fractions. One more example, 1.43. So that's the same as the 3 is in the hundredths place, so that's 143 over 100, and that simplifies to the mixed number 1 and 43 over 100, because 43 over 100 cannot simplify. The next example, and let's just draw a line here. Lots of notes I need to see you get today. Are repeating decimals. Now repeating decimals can also be written as fractions. And the thing about a repeating decimal is it goes on forever, or in math terms, infinitely. Here's one example. I'm going to slide this up. 0.3 with a bar over it, which signifies it repeats the 3-digit forever. This can be written as 3 over 9, and that simplifies to 1/3. Now if you were to take your time to take a calculator and do 3 divide 9 in it, you will find you get the repeating decimal 0.333. Same works with the simplified fraction. 1 divide 3 will also give you the repeating decimal of 0.333 forever. Another example would be 0.7 with a bar over it. That means the 7 goes on forever. 7/9. Now you might say, how can I remember to write this fraction this way? Well, these are in the 10th place value, but that's not the final answer because of the repeating digit. So instead of over 10, you notice I wrote over 9 over 9. So you might ask, well, what if I had a repeating digit of 1, 2? 0.12 with a repeating bar over it. Well, then that can be written as 12 over, instead of 19, there's 2 digits repeating, 99. And that simplifies to 4 over 33. Next section, let's slide this up. It's called non-terminating, non-repeating. Non-terminating slash non-repeating. So that's a number that seems to go on forever, but there doesn't seem to be a pattern to the repeating digits. One such example might be something like this, where the same pattern doesn't repeat, but you notice you got 1, 4, and then 1, 4, 4, and then 1, 4, 4, 4. So you notice you could probably predict what comes next. But this is non-terminating, it goes on forever, and it doesn't repeat. Repeat isn't the same as pattern. Repeat means the same thing over and over again, where in this case it goes from 1 4 to 2 4s to 3 4s. So it's a number that exists in nature, but here's the interesting thing about numbers like this. They can't be written as fractions. Now there's a number here that you're very familiar with. You hear about it in geometry. Probably heard about it in 6th grade, maybe 5th grade. And there's a symbol for it called pi. Now, pi goes on forever without a repeat. And we just refer to pi as a rounded number of 3.14 most of the time. Or some folks refer to it as 11 over 7. And these are simply estimations of the value, or rounded versions of the value. It's an estimation. But pi is still a number that is non-terminating, non-repeating, and exists. So let's look at some unique conversions. We're going to turn to page 12. You had a fraction, decimal, percent card that you glued in your notes earlier in the year, and you may refer back to that for explanation of these conversions, but we're just going to talk about some unique conversions today. So with unique conversions, let's just take a look at how they would resemble different numbers, or the same number, we should say, in different forms. Underline this so we can emphasize the importance. First one we're going to do is 1.15. 1.15 as a percent, that's 115%. And as a fraction, it's 1 and 15 over 100, but it simplifies to 1 and 3/20. The next one we're going to look at let's go a different conversion. Let's start with a fraction of 1 over 9. Now, based on their notes you just had a few moments ago, you may be able to figure out how to write this. But that means that if it's over 9, this digit up here repeats itself, 0.1 with a bar over it, as a decimal. As a percent, if I were to write this to the 10th place, then the 1 keeps repeating, so it's not just 11%, but it's 11.1111 repeating, or we round usually with percents to the 10th place, 11.1%. Let's look at a different one. This one as a fraction of 5/6. Now you can convert this to a decimal by doing 5 divides 6 on your calculator, or long division, 6 into 5. What you find, this is a really interesting one, is you get 0.83, but 3 is the only thing that repeats. Now to change a decimal to a percent, you can multiply by 100 or move the decimal 2 places to the right. And what you get is 83.3 repeating, or 83.3%. Some other unique examples include 0.6 with a bar over it. That as a fraction, you can put the 6 over the 9, but that simplifies. That simplifies to 2/3. This as a percent, well, the 6 is repeating, and you usually round your decimals to the tenths place for this, unless asked otherwise, and you would get 66.6 repeating, or rounding 66.7%. Next one. Let's look at this one. We have 37.5 as a percent. As a decimal, you can take this and divide by 100, or move the decimal place 2 places to the left, convert it to a decimal, and you get 0.37. Now, if we were to change that to a fraction, let's think about something. The 5 is in the thousandths place, so that's the same as 375 over 1,000, and that simplifies. Well, there are, for instance, if you simplify this, and there's 25 will go into 375, and 320, and 25 will go into 1,000. So I would ask you to simplify this yourself at this time and write your answer there. Below this, I'm just going to draw a line, and we're going to make a table. And this table we are going to call the real number system. Before we put any information in it, we're going to make a series of some rectangles inside each other. Let's slide this up, because we're going to talk about how things fit together. So, right here in the middle, I'm going to draw like 3 lines down and across one rectangle. We'll go up. I'll make this one a little bigger. We'll just do 1 line around it each way. And then we're going to make another . Okay. We'll make one more. And then we're going to make a box down here. And before we put some samples inside it, let's identify each category. in the very, very center, the smallest little group component we're going to talk about of sets of numbers are called natural. Natural numbers are your counting numbers. Okay? The next box, right above it, we're going to call these whole numbers because those are the counting numbers and 0. And then the next box, what we've just recently been studying, integers. Above that, rational numbers. And down in here, this little box we made separate from everything, we're going to call them irrational. So in these sets of numbers, samples, natural, that's counting. That's 1, 2, 3, 4, and so on. Whole numbers include one more thing. They include everything that's in here because you notice this box is inside this one. And they also include 0. So whole numbers are 0, 1, 2, 3, and counting. Now integers are whole numbers, 0, and their opposites. So integers would be like -3, -2, -1, 0, 1, 2. And this goes on infinitely, look there, both directions. So integers are whole numbers, or you could say natural counting numbers and their opposites, and 0. And integers are all these numbers that are inside here then in these boxes inside the integer box. Now rational numbers can be other numbers that are positive and negative, which includes everything inside here. So a rational number could be -3/4. But -3/4 can't be an integer because it's not an opposite of a whole number. And it can't be these. Another example would be -0.5. +1/2. 7.56. And other numbers could be many other things like -0.1 repeating, like -1/9. So rational numbers can still be written as fractions and decimals. Okay? Now let's go to irrational. An irrational number cannot be written as a fraction. But irrational numbers are like pi from our notes, or like the non-terminating, non-repeating decimal. Non-terminating, put parentheses around this, non-repeating, just like from our notes. And that could be 0.01, ... This is something that goes on forever, increasing by a 0 between the 1 each time. On the next page, we're going to take some notes on adding and subtracting rational numbers. That's section 1.5.